Alright, we have looked at plane mirror. Now, let's look at what's called a parabolic mirror. What is a parabolic mirror? Well, you know what a parabola is, right? You take a parabola, and here, this is the axis of the parabola. At that point, it's the so-called focal point. Okay? Now, you take that parabola, right? And you spin about its axis. This is the vertex, that's the focal point. You spin about this axis. What you get would be a three-dimensional surface, okay? A three-dimensional surface. That is called a parabolic mirror. What's so special about a parabolic mirror? Well, here's the thing about a parabolic mirror. Suppose I have a beam of light coming in parallel to this line connecting the vertex and the focal point. Okay, after getting reflected, my question is, where is the reflected beam? Okay, now I'm going to apply Snell's law here. I'm going to apply Snell's law. So here's the angle, the incoming angle. Okay, so the outgoing angle would be like this. So in fact, I didn't draw this right. The focal point should be here. Then I imagine another beam also parallel. And I'm going to apply Snell's law once again. So this is the incoming angle. The outgoing angle will be the same. So it goes like that. Here is a reason why we call this a focal point. That one is wrong. Okay, all the parallel beams parallel to this line connecting the vertex and the focal point, after getting reflected by the parabolic surface, would converge at the same point right here. That is the reason why we call it the focal point. Okay, we call it the focal point, and that is a unique feature of a parabolic mirror. Only in the case of a parabolic mirror would you get a perfect focusing this way for all the beams parallel to this line. And what are some of the possible applications of this? Well, first of all, parallel beams. If you have a very distant object, okay, then light coming from that object would appear to be almost parallel to each other. An example would be the sun or the moon. Okay, they're so far away from here that different light rays coming from the sun are essentially parallel, and so you got a beam of sunlight parallel to each other, many beams actually. After getting reflected by the parabolic mirror, they're all going to converge at the same point. Okay, so this is where you're going to see a real image of the sun, by the way. You're going to see or any distant object with parallel light beams coming in. And this is therefore a point where all the energy of reflected light get focused here, right? And so you can imagine a parabolic mirror being used as a device to concentrate energy, light energy from the sun. You have a parabolic mirror, and then the light coming from the sun getting reflected off this very large surface will all be concentrated here. This is where the energy is very concentrated, and you can create a high temperature here. So you can think of an oven. Okay, you can think of an oven powered by solar energy. So all you have to do really is set up a parabolic mirror facing the sun, and then you put something to be heated up here, say a pot of water. You can heat up that water from the solar energy because that's where energy is concentrated. And conversely, suppose I have an object here, okay, an illuminated object here. It's going to emit light in all directions, right? Wherever it hits the parabolic mirror, after getting reflected, all the light rays will go out parallel to each other. Can you think of an application of that? Well, how about the headlights of a car? Okay, so here, let's say I have a little lamp here. Okay, a little halogen light. It's just a point light, and if you don't have anything around it, it's going to emit light uniformly in all directions. But that's not what we want. That's not what we want. We want light beams to be casting forward straight, right? So how do you achieve that? Quite simple. All you need to do really is to put a parabolic reflecting surface behind it. And where do you suppose you want to position the light source? Well, yeah, you're going to position it at a unique point, which is the focal point of this parabolic surface, right? And then after getting reflected by the parabolic surface, all these light rays will become parallel. Okay, so you shoot out parallelly like this. Okay, so that's how you change, a light source casting light in all directions to a light source producing light even only in one direction, that is the headlight of a car. Okay, so that's how parabolic mirrors work. Even though parabolic mirrors are very useful, of all curved mirrors, the ones that are really most widely used are the so-called spherical mirrors. Okay, one reason is because they are really simple to make. It's just part of a sphere. Okay, so we call them spherical mirrors. When it comes to spherical mirrors, there are two types of spherical mirrors. One is so-called concave, the other is called convex. Okay, so in either case, the surface of the mirror is part of a sphere. But in the case of a concave mirror, the reflecting surface is on this side. Okay, so the shape is concave. For the case of a convex mirror, the mirror bulges out like that. Okay, it bulges out like that, and light comes in like this. Okay, so let's take a look at the first case, the so-called concave mirror. Okay, we're going to take a closer look at spherical mirrors because they're widely applied in many cases. All right, first of all, the sphere must have a center, okay? The center of the sphere, which is point C. Point C is also known as the so-called optical center for reasons that will become clear later. And imagine I draw an axis passing through the center of the sphere, and it intersects this point on the mirror, which is somewhere around the center of the mirror. We call this the vertex V. Okay, this axis, which connects C and V, okay, and extends beyond, it's called the optical axis. The optical axis. Now, here's what I'm going to do. I'm going to introduce a beam of light, a light ray, parallel to the optical axis, and a distance h away from the optical axis. Okay, and I'm going to assume that this h is much less than the radius of this sphere. Okay, radius of the sphere, in other words, the distance between C and V. This beam of light, whose separation from the optical axis h is far less than the radius of the sphere, is called a near axis beam. Near axis beam, for obvious reasons. Okay, the reason why I'm going to focus on near axis beams is that allows us to simplify the calculation and drawing to a great deal. Okay, it turns out that for all near axis beams, after getting reflected by this spherical mirror, they're all going to converge approximately at the same point, which is called the focal point. Okay, let's see how that works. Well, first of all, we can figure out exactly where the beam is going to go after getting reflected because we have the Snell's law. So what does Snell's law tell us? Well, here's the incoming beam, right? Here's the incoming beam. Okay, and I need to first of all find the local normal of that part of the plane. So, and of course, from simple geometry, since this is part of a sphere, that is the normal line right here. Okay, normal line right here. So this line is perpendicular to the sphere at that point. By definition, this is the incoming incident angle theta. Okay, and where is the beam going to get reflected then? Well, according to Snell's law, it makes the same angle. Okay, it's going to make the same angle with the same normal line. So that's what I'm going to draw. The beam is going to go that way. It's going to go that way, making the exact same angle. Okay, this angle is also theta, right? So it crosses the optical axis at that point. And what I want to know is, where is that point? Okay, how far is it from the center of the sphere, and how far is it from V? Well, it turns out that if h is a lot less than r, here r is the radius, I can say that this point is roughly midway between C and V, between the center of the sphere and the vertex. Let's see how we can prove that. Well, as a matter of fact, if you look at these two angles, you know they're the same. That is the Snell's law of reflection. But you also take a look at this triangle. Look, 1, 2, 3. Okay, look at this triangle. This triangle, I have an angle there. Okay, I have an angle there. I don't know what that is, but I do know that if you add this angle phi plus the angle theta, you're going to get this angle, right? You're going to get this angle. How much is this angle? That's theta plus phi. Theta plus phi. But wait a second, on the other hand, we know this angle is equal to 2 theta, isn't it? Is equal to 2 theta from here to there, because this is 2 theta, which is equal to that. So this is 2 theta. So what do you think phi is? Phi really is just theta, because phi plus theta equals 2 theta. So phi equals theta. Okay? And what can you say about this triangle here? What can you say about this triangle? It is clear that this side would then equal to that side. Okay, so from C to that point, which we call F, the distance between C and F is the same as the distance between F and that point. All right? Now, on the other hand, okay, on the other hand, remember H is very, very small compared with the radius R. In other words, all these angles are extremely small. Even 2 theta is very, very small. So the way I draw it, I already exaggerated. Theta shouldn't be really that large. I draw it so that you can see it more clearly. But in reality, 2 theta is very small. So if you look at this line here and that line there, it's a very, very, it's a triangle it's got a very, very long arms and very small base. In other words, this length and FV must be roughly the same. Okay, so once again, CF equals that, but that is roughly equal to FV, right? Because the angles are very small. So what did that tell you? It tells you CF and FV are roughly the same as one another. Now the total distance between C and V is what? That is the radius of the sphere, right? Because C is the center of the sphere, and therefore CF and FV are both equal to about half of the radius. So the distance between that point F and the vertex is about R over 2. Now you got to understand that that point is where any near axis beam must cut across when it crosses the optical axis. Okay, you see, I didn't really specify H. I didn't say how much it has to be. I just said it's going to be a lot less than the radius R. So we're looking at a near axis beam. It looks like all near axis beams, roughly speaking, would pass through the same point F, which is midway between C and V. And this is why we call this the focal point. Okay, the focal point. All parallel beams, parallel to the optical axis and near the optical axis, after getting reflection by the spherical mirror, must pass through the same point. This, in fact, is an approximation, as you know, because these two distances are not exactly the same, but it becomes exact if the spherical mirror becomes a parabolic mirror. Okay, becomes a parabolic mirror. We can remove that restriction that H is a lot less than R. But, near the bottom, a spherical mirror and a parabolic mirror are not that different. Okay, a parabolic mirror will extend like this and like that. So if you go very, very far, it's going to be very different from a spherical mirror. But at least near this part, they're almost the same. So that is why you shouldn't be surprised that a spherical mirror would roughly give us, a focal point, just like a parabolic mirror would. Okay, and the distance between the focal point and the vertex is called the focal length, F. F is therefore R over 2, approximately R over 2. Okay, so we learned several concepts concerning a spherical mirror. We have an optical axis, right? And we have a near axis beam, and then we have a focal point, which is roughly midway between the optical center and the vertex. Okay. Now, next, with this in mind, we're going to look at how to draw the location of an image formed by a concave mirror. The way we do that is, imagine there is a point, which is our object. We want to know how light beams coming from that object after getting reflected by the mirror would converge. Okay, to this end, I would need 2 light beams, right? At least 2 light beams to see where they converge. Okay, I already know how to draw one light beam, which is a beam that is parallel to the optical axis. I know exactly where it's going to go. It's just going to pass through the focal point, okay, which is midway between C and V. I need another rule that tells me how to draw another special line. Okay, special line. In fact, there are a couple of ways, easy ways you can think of. Okay, one is, suppose I aim directly at a focal point. Okay, I aim directly at a focal point. So I draw some from here through F and then passes on. Where do you think it's going to go? Well, a beam that is parallel to the optical axis will pass through the focal point. And here's a beam that is parallel to the optical axis. It's going to pass through the focal point. So as you extend this beam beyond F, it hits the mirror. It's going to go out parallel to the optical axis. So that gives you a second beam. But there is an even easier way to do that, and that is you're going to aim at point C. Now, what do we call point C? We call it the optical center, right? The optical center. And there is a reason why we call it the optical center, because after all, if you hit a beam, okay, if you start from a certain point, say this point, okay, this point, and you aim at the optical center, you draw a line that is aimed at the optical center. This beam really is a radius, right? This is a radius. So this is already 90 degrees. Right? If it's 90 degrees, after reflection, it's going to go out also at 90 degrees. So in other words, any beam that passes through the optical center after getting reflected by the sphere would bounce right back in the opposite direction. Okay, it is not going to go any sideways, it's going to bounce right back. This is the reason why we call it the optical center. And this is not an approximation, it is exact. It's because of the spherical nature of the mirror.